In the previous video, I demonstrated to you how you can find the cumulative distribution function and probability density function of a related variable. Basically, we said for a continuous random variable x with a cumulative distribution function f of x, where x is connected to y by the equation y is equal to, say, h of x, we can find the cumulative distribution function of y by g of y is equal to the probability that y is less than or equal to y, which in turn will be equal to the probability that h of x will be less than or equal to y, just replacing h of x for y, since y is equal to h of x. And here we can inverse both sides so that we have the probability that x is less than or equal to h inverse of y. And the probability that x is less than or equal to h inverse of y is the same as the cumulative f of h inverse of y. So this is how we find the cumulative distribution function of y. Now once you've obtained g of y, which is the CDF of y, you can now be able to get the PDF, that's the probability density function of y, by g of y is equal to the derivative with respect to y of the cumulative g of y. So I have another example here just to give you more clarity on how we do this. So here's the question. It says, the continuous random variable x has probability density function f given by f of x is equal to a sixth of x for values of x ranging between 2 and 4 and 0 otherwise. The random variable y is defined by y is equal to x cubed. Show that y has probability density function g given by g of y is equal to 1 over 18 of y to the power of negative a third for values of y ranging between 8 and 64 and 0 otherwise. So let's start with that first part. So here they want us to find the probability density function g. So first of all, I'm going to find the cumulative distribution function of f. So I'll say for some value t, f of t is equal to the integral from the lower limit 2 up to t of a sixth of x with respect to x. And this is going to give us, integrating, we get 1 over 12 of x squared. And that's for the limits 2 up to t. Then I can substitute t here to get 1 over 12 t squared. And I can substitute 2 here, which is a 12th of 2 squared, which gives us a third. So it's minus a third. So therefore, we can say that the cumulative distribution function of x is a 12th of x squared minus a third, and that's for values of x between 2 and 4. So that's what we have. Now that we have the CDF of x, we can now find the CDF of y, which is g of y. Now for g of y, we know that that's the same as the probability that y is less than or equal to small y. And we know that this is the same as the probability that, since we are saying that y is equal to x cubed, in place of y, I'm going to place x cubed. So it's like this. And that will be the probability that x is less than or equal to y to the power of a third. Now, the probability that x is less than or equal to y to the power of a third is the same as the cumulative f of y to the power of a third. Now for f of y to the power of a third, we substitute y to the power of a third here. So therefore, this is the same as a 12th of y to the power of a third squared, and it's minus a third. We can simplify this, and that's going to give us a 12th of y to the power of 2/3 minus a third. So here we now have g of y, that's the CDF of y. So we'll be saying here g of y, that's the CDF of y, is equal to a 12th of y to the power of 2/3 minus a third. And that's for values of y. And for the values of y, we are saying, since y is equal to x cubed, when x is equal to 2, y will be equal to 2 cubed, which is 8. So we have the lower limit here as 8. And when x is equal to 4, y is equal to 4 cubed, which is 64. So I'll have 64 here. And then it'll be equal to 0 for values of y that are less than 8. And it'll be equal to 1 for values of y that are greater than 64. So that's the CDF of y fully defined. But from the question, they want us to find the probability density function of y. So that's small g of y, which we find by differentiating with respect to y, g of y. So that'll be equal to the derivative with respect to y of a 12th of y to the power of 2/3 minus a third. And if we differentiate, we are going to get 1/12 of 2/3 of y to the power of 2/3 minus 1, which is minus a third. So that's 1/18 of y to the power of minus a third. So this is the CDF of y. So we can write it as g of y is equal to, and here that will be 1/18 of y to the power of minus a third, and that's for values of x ranging between 8 and 64. And it will have a value of 0 otherwise. And thus we have proved it as they wanted us to do. So that's it for this part. Now the other part of the question says, find the expectation E of y. Now for the expectation, that's E of y, we will make use of the PDF of y to say that's the same as the integral from the lower limit 8 up to 64 of y of 1/18 of y to the power of negative a third, and that's with respect to y. That's the same as 1/18 of the integral of y times y to the power of negative a third, which is y to the power of 2/3, and is with respect to y. Now this is 1/18, and that's off. When we add 2/3 plus 1, we get 5/3, so that's 3/5 here of y to the power of 5/3. The limits are 8 to 64, we shouldn't forget, so 8 to 64 here. Alright, so that's 1/18, and that's off 3/5, that's multiplied by 64 to the power of 5/3. So that's 3/5 of 64 to the power of 5/3, and it's minus 3/5 of 8 to the power of 5/3. So here I'll factor out 3/5, and if we multiply it to 1/18, we get 1/30, and that's off 64 to the power of 5/3, which is the cube root of 64 to the power of 5, which just gives us 4 to the power of 5, and it's minus 8 to the power of 5/3 is the cube root of 8 raised to the power of 5. The cube of 8 is 2, so that's 2 to the power of 5. So this is equal to 1/30 of 1024 minus 32, and 1024 minus 32 is 992, and 1/30 times 992 reduced to lowest terms will give us 496 over 15. So this here is the final answer for the expectation, and that's how we do it.